Hi everyone, today we are continuing with the Inflationary Cosmology, the third video, and we are talking about the radiation and the matter-dominated era of the universe. For the flat case, for the assumption, we claim that the universe is flat, we neglect the curvatures, which is actually corresponding that we are studying in the flat space. The flatness is due to our assumption, and the assumption is just a requisition. The requisition so as to understand the dynamics of the flat potentialized universe. So the matter distribution around the universe, for the assumption of ours, for the sake of the cases to be easy and the simplicity, the material distribution around the universe is uniformly distributed. So we are just checking the distribution of the material or the energy densities corresponding to the fields. The fields can be electromagnetic fields or the mass distribution, doesn't matter. And we are just solving the equations, the Friedman equations we derived in the previous videos, which is actually the first inflationary cosmology video. Okay, for the next video, I am so excited to announce the topics. Actually, I will illustrate and I will demonstrate in the next video that the curvatures. So the cases will be open and closed universe respectively, and we will do the same thing, the solutions respectively to the radiation dominated era and the non-relativistic matter dominated era respectively. And the solutions will be a little bit different. By the way, it is definitely, certainly different, which is ISOR, which can be indicated easily that the expansion is determined by the material density and the curvatures around the universe, which the curvatures are global curvatures. The curvatures are not local distributions, but it's actually the whole shape, the whole structure of the universe. This is actually what we are investigating in the next video. So for today's universe, permit me then to enlighten about what's the era such that the radiation dominated era and the matter dominated era is corresponding to. We are studying the standard cosmology model, which we neglect the pressure of the cosmological fluid, which is actually easy way to solve the Friedman equations, because the Friedman equations for this, in this claim, in this assertion, they do not include the contributions of the pressure effect of the fluids. So we are only interested in the material and its presence in space-time. Well, what kind of space-time? Of course, it can be dependent to the geodesic, which is actually the metric. If we were interested in the energy densities, the pressures, and the curvatures, we would be actually talking about the relativistic effects, such that the metric in here, the coordinates in here, are not the coordinates in that place. So the space is not isotropic anymore. But we assume that the pressure on the space-time is zero, in the background is zero. And we will focus on that. So the radiation-dominated era of the universe is corresponding that from t equals 0 to 70 plus or 70,000 years, plus or minus 10,000 years, we have uncertainty. And this is actually the standard model, which we are assuming that the universe has started to expand, the inflation, at t equals 0, called Big Bang. And afterwards, the inflation is so fast, there is nothing else to slow down the expansion rate of the universe, so it grows exponentially. It's really fast. And how much, the amount of time that is required to reach the universe, the maximum size, or maybe the amount of time in the era of the universe, which we call the inflationary era, the inflation era of the universe, is about 10 to the minus 25 seconds, and 10 to the 35 seconds between those values, and the energy corresponding to this shape, to this volume of the universe, is 10 to the 16 giga electrovolts. Imagine how terrible the value is. I mean, it is enormous, but it is normal because in the early times of the universe, the quantum fluctuations are important, and it takes place. And well, we do not actually doing the same thing in the radiation-dominated era, because afterwards, after this kind of process that were occurred in that era, which is inflation era, which is actually exponential, the prerequisites, the fundamental particles and their nuclei are formed. Actually, the quarks, and if we go deeply, then we will reach that we will easily indicate that they are actually the interactions of fields, the Higgs fields, and the others. We don't know yet, because we do not explain the era, the chosen era of the universe, respectfully to the pressure of the cosmological fluid. We are interested in the events, the dynamics afterwards this era, which is actually called the Big Bang. Afterwards the Big Bang, the radiation-dominated era, the universe is filled with plasma. It was actually the radiation soap. So everything, there is no massive objects yet, or if they are not, well, the mass, of course there are, because they are nuclei. If we neglect the question what the hell is the mass itself is, the definition of mass is determined by us, you know that. So I am ignoring this question for now, for the sake of the cases to be more clear to understand. And there are, of course, incorrigible questions towards, well, striking my mind as I am representing this video, but I am just trying to prevent them to remind me to, yeah, okay, you got that. The question is, we are interested in how much time will it take to grow in the radiation-dominated era, and the size of the universe after this amount of time is the question. And as we go further away from the t equals 70,000 years, plus or minus 10,000, we are going to actually have the mixed case where the massive objects and the radiation are mixed together in the universe. It's filled with both of those densities. Radiation itself has the density along the universe. What we are talking, what kind of density? This is actually the energy and the momentum of the photon. So, well, if I record the electrodynamics video in the future in English language, I will be easily dare to say that we have talked it before, but not for now. We are actually interested in the momentum stored in the electromagnetic fields, and which are actually the cavities around the universe, small tiny cavities. And imagine in this cavity there's a radiation, what we call the oscillatory electric and magnetic fields. They are oscillating rapidly. The amplitudes are so fast, so big, and the frequencies are so fast, which is corresponding to the higher energies. But afterwards there are interactions between the fields, which are causing that the materials with what we call or define mass are just interacting towards our case, and which it takes place in the mixed case and the matter-dominated universe, such that stars and galaxies are just being formed. The first primordial galaxies, can you imagine? Or maybe the black holes. Not the black hole, but permit me then to call this bizarre things like the space-time regions, or the locations, the coordinates where the massive objects and the other kind of densities, the field densities of the universe, are just densified. Imagine every of these particles, fields, even if it's a particle, we have the field. If we are studying classical mechanics, they are particle, point objects, doesn't matter or not. But if you are studying in the relativistic theory, everything is the field. So you are writing down the entire action integral and you are just solving it. How do you solve it? Well, actually you are using the Lagrangian solutions, the Lagrangian formalism. If you know the action integral, then you know the metric. And well, the s squared or the tau squared, depending on what kind of frame of reference you are talking about. It might be space-like, time-like, or light-like, the null ray. Okay, which is actually the light cone. Imagine here is the y-axis and the x-axis. Oh, sorry. This is actually the vertical line is like the proper time, and this is actually the space components. And with the 45 degrees of angle, there are cones in the both positive and negative sides of this axis. There's a light cone. You can well, I'm improvising, by the way. You can imagine that like that. So which we call it. This is actually the 0 point actually, and the event is happening in that time. So the solutions, of course, will be dependent into the trajectories you are talking about. Okay, for our case, by the way, we are recording. I hope. Let me. Of course, we are talking about the radiation and the massive objects. So if you remember in the first inflationary cosmology video, I was talking about the nearby galaxies and the observation towards them, which actually is based on the hydrogen lines and, for example, the spatial wavelength, such that 21 centimeters wavelengths, or maybe supernovae type 1a. Those are just the sources you can compare the consequences or the results of your theory with the experimental data, the observational data, by the way. We are just dealing with that, and we observed nearby galaxies, as you remember, and we just calculated the rate of the expansion. Well, it was actually done by claiming that the first assumption of ours was in that video that the gravitational field, which is actually produced by the presence of the gravitational material inside of the Gaussian surface, and which was actually static gravitational material. They were distributed uniformly and homogeneously, so they were static on the first time. So they produce a field, the potential distribution. So we had a test particle which were actually which was actually bounded into the gravitational potential, so it cannot escape, but have an orbit around it, depending on the eccentricity, depending on the angular momentum, and depending on the energy from the center of mass distribution. It has some closed or maybe unclosed universe, path, right? A trajectory. It might be closed orbit, or maybe it might be something elliptic, something like that, depending on these variables I told you a few seconds ago actually. So we were actually determining the behavior of this particle, the motion of this particle. It is easy to determine that by using a Lagrangian and a field theory. It doesn't matter. It's your choice. The important thing was that after some amount of time, the sphere, which is actually present in the Gaussian surface is where the particle is located at the given time, some constant time, is just in that place, and it starts to grow up. In that case, the gravitational field is actually non-conservative, so you cannot write it down as the divergence of some vector field. So it's going to be curl. I mean, it's going to have the curl, right? So the curl corresponding that it's not stationary anymore. So the field it produces, if you can imagine with the field lines, they will be bent as the source of the gravitational material, the gravitational field, sorry. If the material inside of this sphere is starting to move, which is corresponding that it's non-conservative now, the field it produces is actually fluctuates. And the field lines for improvisation for representation of the strength of the field around it, around the nearby points of the sphere, which is growing as the time itself elapses, the lines and the density of lines, which we call flux, will not be the same as it was in the previous stationary gravitational field case. So the field is non-stationary, which is not conservative anymore. So the field lines, as the sources of the field moves, the field lines are curved, bending over. They are going to be, they start to being curved, right? That is actually the point. So we investigated the case where the sphere and the radius of it is just growing up, which is representing that you can imagine this is like a sphere and there are dots on it, which is actually corresponding to the nearby galaxies, which is actually the cluster, the galaxy cluster, and we are inside of the sphere and we are observing the nearby galaxies around us and which we were surrounded by. And imagine when, because of the inflation of the universe, there is some kind of energy. So nothing in the universe is stable. So they are just, the distance between those galaxies are just growing up. Question: is the expansion or the rate of the expansion, is it the same in all directions? Is it homogeneously distributed too? The question is that. For now, we assume that it is, but it depends on the material density and distribution. Why? Because the material density causes the gravitational fluctuations in space-time, which is corresponding to that the energy densities, energies are just fluctuating and non-stationary anymore. So the curvatures in here will not the same as in that place. So depending on the coordinates are not varying uniformly and in the same way as in that place or in that place. It will vary too, which is actually corresponding that the proper times will be different too. Because here is metric, okay, here is some metric, and in that place there is some metric. If the metric is determined by the material, the field, the time, which is actually representing the entire trajectory, will also be affected by the presence of these fluctuations. If those fluctuations in here and in that place are different, then the proper times will not be same. So we are not studying in actually space-like trajectory, but it's going to be time-like trajectory, or maybe light-like, or between them, depending on the sign of the metric, ds squared, plus or minus, greater or less than 0. That's actually the key problem. For the sake of the simplicity, we assume in the Inflationary Cosmology 1 video, I assume that the sphere, the Gaussian surface, was growing up because of the kinetic energy that were coming from the Big Bang. The theory of ours we are doing right now is claiming that the universe starts to expand at t equals 0, the Big Bang. Okay? So the kinetic energy is coming from that, like a spring constant and this mass. When you push it towards the wall, which it cannot pass through that place, we are not doing quantum mechanics. It might be tunnel into this direction, which the potential is too much, not infinite. Well, finite potential, imagine that, like a box, right? The potential box, or maybe, it doesn't matter, plus or minus, there's the potential. So the flux of probability, which actually representing the particle, the wave function, right? The wave function is representing a particle because those are waves of matter. They can penetrate. In classical mechanics, they can't. It must be reflected back with 2 times greater than the momentum. Or if it were a photon, the momentum is p over c, right? But if it's reflected, no transmission, 100% reflected, then the momentum is 2 times p over c, the momentum divided by the light speed of light. Might be. But we know that electromagnetic waves cannot actually do this thing. So the amplitudes will be changed by a factor that's, for example, imagine here is a boundary, here where the incident wave is coming from, and which after this boundary, here is the place where the transmitted wave propagates along. So when the wave comes, it reflects some of this part of it. So it transmits also. So by using the Maxwell's equation, and by the way, the superposition principle of waves, it doesn't matter what kind of topic you are interested in. Superposition principle is the key point. In this area, there are incident wave and reflected wave with different kind of amplitudes and different signs of the wave vectors, which are represented at the direction of the propagation. And in this place, there's a reflected wave that the amplitude is changed by a factor, well, depending on the magnetic and electric permeabilities of this mediums, right? Anyway, for the I want to talk, yeah, okay. But I should not dissuade you from cosmology. The essential intention of ours for today is to investigate the behavior of the galaxies in the matter-dominated universe and the radiation, which is actually called the electromagnetic waves in the radiation-dominated era of the universe. So where are my pencils? Oh, shit. All right. Sorry. I just choose the wrong markers. You can see that, right? Inevitably, they do not vanish. I can't remove them. So maybe using alcohol. Oh yeah, smells nice. Okay, the last time we were talking about the in the inflationary cosmology video, actually the first one, the second and first order Friedmann equations, right? In the second video, I was actually derived the equations, derived the second order Friedmann equation by taking the first time derivative of the first time derivation, first order differential equation of Friedmann equation, right? So we also checked that the cases where the second order Friedmann equation does not work, it can't work, I mean, and it was actually the radiation case. If you watch this video, then there's no problem. But it works in the presence of the non-relativistic material, right? In the flat case, which the curvature k corresponds to 0 for now. And recollect that we have h squared is a dot of t divided by a of t, and which is actually 8, what kind of pencil you are, 8 pi g divided by 3 rho of t minus kc squared divided by a squared of t, right? Depending on the material you choose, the density is changing. So we assume that the gravitational field was increasing. The radius of it is just growing up as the time passes. So the radius of the sphere, which is actually represented at the gravitational field, and the Gaussian surface, which is there so as to understand the dynamics of the particle in the given fields, which the fields are just produced by the presence of the material, the massive materials inside of the space, which the material is just embedded. And those materials are actually the distribution of the galaxies, the other galaxies in the cluster. So just as the time itself elapses expeditiously, the clusters just started growing up, and the radius of it is increasing. Why? Because there's a kinetic energy that is coming from the Big Bang, and we assume for the presence and for the sake of the simplicity of this theory that the kinetic energy is coming from the Big Bang, and which is actually turning and converting, transforming to the potential energy. It is like a spring and mass system. It's like an oscillatory system. We expected until 1998 that the universe to expand until some point, which is actually the critical point, which occurs in a critical time, where at that time, the density of radiation or density of the non-relativistic matter is equal to the density of radiation. Or you may imagine that the kinetic energy is just ends up and there's some point which the total energy is 0 and starts to be minus. The total energy is the minus sign, which is corresponding that the universe is just collapsing together and entire universe is just collapsed into the one point. So it's just imagining again, and just starts to expand again. The inflation, which the case is called, which the case itself is called the big crunch case, and this is the case we intend to investigate in the next video in the open and closed geometry of the universe, called K is not 0 greater or less than 0, corresponding that the curvatures that are occurring right now, which the fields are distributed in the Riemannian spaces, such that the Robertson-Walker metric or the Minkowski space. Okay, now it's not a topic. Today's purpose is to do the expansion, the rate of the relation of the expansion depends on the material you have chosen in the given era of the universe, as I have mentioned in the very beginning of this video, and which the K is 0 in here in this video. You might be looking at the people doing this, but they are solving Einstein's field equations. We are not doing it yet because I did not record anything about the tensor algebra, and I have intentions to do it too. And afterwards, we will be able to derive the equations of cosmology in Einstein's field equations. Actually, well, it's actually the action integral, right? So action integral can be anything. So there is some arbitrary constant m, and we have the integral, which is actually the fourth degree, so it's actually here is the minus g represents the metric, represents the curvatures, pseudo-Riemannian, by the way. But in the simplest form, let me say this is well, if there's some field, the dirt. Sorry. Well, x is the components of the position, the Lagrange, and phi is the potential. So the phi and the derivatives of phi and the proper time. This is actually the action, and you are writing down the entire thing here. So it must be the Lagrangian, by the way, the Lagrangian function, or it can be 3 space components and 1 time component. For the consistency of units, we may add MC. For the consistency of units, m is the arbitrary number. In classical theory, it's just the mass of the particle. We do not do it right now. You can do everything from here, okay? Okay, okay. We have derived that the relation, let me use the black one, the relation that the expansion of the universe for non-relativistic matter is different than the radiation. Of course, it's supposed to be, because the gravitation tends the universe to be slowed down because the gravitational attractions, and which is actually the main reason that we have a kinetic energy at the very beginning, the Big Bang, and it becomes the potential energy. But as the particles and the other galaxies, stars are just keep forming, the gravitational attractions are increasing. The number of gravitational attractions you can't imagine. There are actually infinite numbers, right? Because any field or anything with mass is just interacting with the other. So they are just trying to pull up each other in the viscous fluid. The viscous fluid is actually the space. And if you imagine it like a dark energy, yeah. We do not do it right now. So this is actually rho m, 0 divided by a cube of t. It was our relation, right? So the material density is, let's say this is m, the massive mass, for matter actually, is proportional with the volume, or maybe the length cube, right? So I am just deriving the equations for taking the first time derivative of it, rho mt, which is which I am actually looking forward to understand the rate of the expansion with respect to the density of the material. Rho m dot is the first time derivative of this function, which is minus 3 rho m0. Well, yeah, not to worry about that. Divided by a to the 4, right? And the derivation of this, this is a dot of t. In terms of writing that, let me write down it in, well, I intend to see the relation with the Hubble expansion rate. So I can write down as minus 3 rho m naught a dot over a as a function of time. And here is a to the cube, right? So here is actually rho of t, this one. And here is actually the Hubble expansion parameter. So rho of t, rho dot, for non-relativistic matter as the universe expands, is minus 3 rho m t h of t. As it increases, as the Hubble rate is increasing, the density changing, the ratio of the relation, which shows us that as the universe expands more faster or rapidly, the density is decreasing by a factor like that. Okay? And well, this is actually what we expected, because why? As the sphere, the Gaussian surface is expanding, as it expands, sorry, the mass per unit volume is decreasing, right? Because of this relation. It's supposed to be. And as you can see, the Hubble parameter is proportional with the density of matter, by the way. So, more the material density in here, as you see, is greater than the Hubble expansion rate, but we have the problem here. It affects better than this one, because it is the root and this, okay, and the minus sign, by the way. So, putting those equations now, we are just solving it again. That's the Hubble parameter h of t squared equals a dot t over a of t squared equals 8 pi g over 3 this rho m not divided by a cube of t, where the curvature's k is 0 for our assumption now. Okay, we are just solving this equation. By the way, let me check if we are not recording. And we are recording. I can get closer into here to make it visible. Yeah, better. So, using these equations, well, we are not doing calculus. Just multiplication, right? And divide. Our derivation. Well, okay, we are doing calculus, but not hard. Just the derivation. Oh. It is easy because we assume the curvatures are 0, and the cosmological fluid does not change the density, the pressure on space-time. If there were pressure, yeah, you can solve it. We will see in the next chapter for open and closed universe, the solutions are hyperbolic. Hyperbolic since and sinh and the cosine hyperbolic. Dependent guy. Okay, not now. So I'm just take the root. A dot, by the way, I'm getting tired. A dot over A. This is some constant here, 8 pi g rho m naught. Let's say, okay, whatever. Do not say anything. So here is, we come in. Well, here is the a squared, right? 1 over a squared. So there is the 1 over a cube. This is the reason why. I have to write down everything from point to point. This is squared and this is squared. Otherwise, I'm going to confuse. Rho m naught divided by a cube of t. And it's more clear, I think. That's better. It's better to do it. So it will vanish from here. And there's a. So I'm taking the root. By the way, you must be here. You must be here. Rho m naught. And 1 over a to the half second. And which is actually the first time derivative. I am just replacing, writing in notation that's the ordinary derivation dA over dt. It's an easy integral, by the way. So a to the half t dA of t equals this constant here, 8 pi g over 3 rho m naught to the half, the root of it, dt. I'm just integrating, and the result is, well, we assume that here is the entire right hand side is the constant. So a to the 3 over half, right? And we have in the denominator, sorry, 2 over 3 dat. Well, from let's say from 0 to the a, 0 corresponds that the first radius. If it were the radiation dominated era, I may call it 0 because at the Big Bang t equals 0, the scale factor is 0. So it's like a point where, well, it's not a point, it's singularity where the universe starts to begin, start to expand, begin to start. Oh, okay. Well, okay, there's actually the constant here, c. But I just want to see the relation between the scale factor and the time, the process. Depending on the time, we will be able to understand the relation between the expansion rate and time, and by using the time at the end of this inflation with given material density, which is non-relativistic matter density, you will be able to find the total radius of the universe, the horizon distance, this stage. I got it in. Yeah. Okay. So I'm just taken or set the integral constant to be 0. Okay. So this is 8 pi g over 3. The root of it, 1 over 2 times t. And by the way, I can put this constant to the right hand side. 3, yeah, it's better. I want to see the relation between them. So we have a of, well, this is by the way function of time. A of t, as you can see from here, equals 3 over half to the 2 over 3, 8 pi g over 3 to the 1 over 3 times t to the 2 divided by 3, 2 over 3. So the relation is that a of t is proportional with the time to this one. For matter-dominated universe, which the curvatures are 0 for our assumption, let's say this constant I would like to call it something, okay? This thing, let us call it gamma matter, is a constant, so it has nothing to do with the derivation or the functions. Are they recording? Yeah. It has nothing to do with the functions. It doesn't change my results. Cleaning the board right now. Now we are interested in the Hubble parameter. And by the way, there are good news. We know the function, the scale factor, depending on time, as a function of time. So recollect. Sorry, I forgot that. Okay, it's better. Recollect the Hubble parameter was h of t was a dot of t divided by a of t. So writing down the a dot, we have 2 over 3. Oops, sorry. Some constant here, gamma m. This one, and we have t. I don't know. So it is. Let's check. We are doing math right now. All right. So this is in here, t to the 1 over 3. You can see the math, right? The power of math. This is math. Oh. Okay, so a dot is here times 1 over a. 1 over a is 1 over a gamma m t to the 2 over 3. So they will vanish here. Here is t, so 2 over 3t. Thus, we have found that h of t, let's say this is the matter-dominated universe, 2 over 3t. That's what we expected. So the time is actually in here, 2 over 3h of t. For given time, we have actually t naught. We measure it someplace. We ignore the conformal time theory right now. We have this, and let me write down the values of it. I have calculated. Not calculated. I have just searched from the internet and just found this value of it. For matter-dominated flat universe, the Hubble parameter is h naught, the little h, times 10 to the 10, where h is 72. If I put that here, Tm, I just calculated it, okay? 2 over 3 times 0.098 times 10 to the 10 divided by 3 times, and which is actually, you can do it, 9.1 times 10 to the 9 years. Okay, so this is actually it's about 9 billion years for matter domination of the universe. If we study the Big Bang assumption, very beginning is the Big Bang, it takes this is actually the lifetime. Okay, for matter to be dominate, this is actually the time required, the amount of time required for the dominance of the matter, non-relativistic matter. We do not mean that the universe is filled fully with the non-relativistic matter. We say that the distribution of the material inside of the universe, the entire universe, is mostly including the non-relativistic matter, and it takes, for the dominance of it, is about amount of such time. It is actually 9 billion years from the Big Bang. So what's wrong with today's expectation, the expected value? It was actually the theory. We were actually looking forward for the solutions that the universe is just expanding into some radius, and afterwards it collapses back. So the collapse is actually the reason why, for example, if you pull the spring, then it pulls you back, right? It's because of the restoring force. So the potential is actually, well, for the uniform field, we know that the potential is, the minus gradient of some potential with some coordinates is giving you the field, the force. So larger the potential, greater the force in the opposite direction, which the potential is increasing, which it diverges. Okay, so this is the time required. So let us calculate the where's my header? Over. Yeah, it works. So the time, we have found that. If you know the time, then you can find out the horizon distance, which is actually the total radius after this amount of time elapsed. The universe reaches its maximum size, and which is actually what we call L sub p, length, physical length, and as a function of time. Imagine here is the units of time, seconds, for example, or years. If I multiply every side with the speed of light c, which is actually in the units of length over time, so times will be vanish, and everything left behind is the units of length, meters, right? It is actually 2c over 3h t naught, and which is actually in here ctm. Yeah. So I'm not interested in those terms actually. I'm really tired. Yeah. Well, I didn't calculate it yet. But I'm looking forward for the numbers, by the way. That's the other thing. Oh, yeah. All right. So this is actually the horizon stage. We have, well, let's multiply both sides by 3ct, right? Yeah, I know. So, LP of t is, oh, yeah, sorry. Here is the unit of, for example, meters per second, and here is 1 over second, so seconds will be vanished. So this is actually the units of length. So this is ct, 3ct, right? Any problem with that? I'm alone, by the way. Oh, I am asking, right? Sorry. So this is actually the rate of it. And how you calculate 3 times speed of light, 3 times 10 to the 8 meters per second. And this, by the way, you have to use it years. Instead of years, you should use seconds. and you find out, okay, this is actually Tm in here, what we have calculated. I'm tired, man. Well, I'm not in school. I am not studying 14 hours as I am in the school season. We are in summer, semester. But it's hard because I'm still studying. 5 hours, 6 hours. It's like a half. Yeah. Normal. Yeah. Why? Because I have completed. And what do you do on the other entire time which is left behind? I'm studying, reading. Just that. I'm sleeping, by the way. Yeah, that's true. Because in the school season, I cannot find an opportunity to sleep. Maybe 3 or 2 hours in a day, in the week time, not weekends. Maybe 5 hours if you can, if it is possible. Yeah. That's for the matter-dominated flat universe. That was our case. Yeah, I think we can take a look for radiation-dominated era and let's finish that. Are we still recording that? Oh yeah. Alright. For radiation-dominated era, it is much more easier to do. Why? Because I don't know. It's shorter. Oh yeah, it is because it's radiation. Clear. Because we have strong theory behind the radiation. Everything, every indication, every deduction towards the radiation is just the favor of the Maxwell. So the Maxwell's equations are key problems, and we will investigate in electrodynamics, which I am desiriously looking forward to record in 1 month, August 2024. We will investigate everything. Relativistic, of course, relativistic. This is a relativistic case, of course, yeah. Yeah. All right. Let's solve it. Let's do it. All right. It's better for it to stay here. I'm going to use it. And afterwards, we'll be ready. A of t, right? Okay. For domination of radiation, we have the relation. I have found that in the previous video, both first and second videos of inflationary cosmology, you can find the derivation of it. The radiation is decreasing by a factor of a to the 4th, the scale factor, a. This is actually the initial density of radiation at the first time you are observing it. It is some constant. Some people tend to write it like a naught to the 4th is a constant number. And if it were the matter-dominated case, this is 3, so this a naught would be 3. I assume it to be 1, like I set it to be 1. We are looking forward for the functions, right, variables. So as the universe expands, I am looking forward the ratio of the change in. This is the first time derivative of the radiation energy density, radiation density, not energy, yet. Which is actually -4 rho r naught divided by a to the 5, right? And a dot of t. And writing down again in terms of Hubble parameter, which is respectfully represented as a function of time. What's wrong with you? You little shit. Minus, I prefer to use chalk, but I'm at home. Otherwise, mommy kills you, right? Because of the dust. Chalkboard, is the favorite thing of mine. It's something assiduous. I miss my chalkboard in the school. Yeah, that damn it chalkboard. -4 rho radiation 0 divided by a to the 4th and a dot of t divided by a of t, which is actually -4 rho of t h of t. We are going to find out this. So putting that into the first order Friedmann equation, you can't use the second order for radiation case. I proved that in the second inflationary cosmology video. I proved. Okay? So h squared, this is a dot squared of t divided by a of t squared, which is 8 pi g over 3 rho radiation 0 divided by a to the 4th of t. So they will vanish in here, which we have a dot of t, which is dA t divided by dt, 8 pi g rho r naught divided by 3 to the root, is it? Yeah. Is it the root times 1 over a. And so a of t dt, oops, dA equals 8 pi g rho radiation 0 divided by 3 to the root of it times dt. I am taking the integral. You know the limits? Well, we are studying the radiation case. You can easily take a naught, a at t equals 0 is 0. The universe is in Big Bang theory, it is singular point, which it has no size. After the inflationary era of the universe, it is about, well, the size of the universe is about a marble, and the density was about 10 to the 81 grams over centimeter cube, and the energy corresponding to this marble into this volume is about 10 to the 16 gigaelectrovolts. And the time it decayed, well, the amount of time this events happened is about 10 to the minus 35 seconds. It's about the Planck length, Planck volume. It is, yeah. Why? Because those are the conditions where the gravitational fluctuation, the quantum gravitation and its fluctuations takes place, and which we cannot observe still. And well, why we can't observe? Because they do not interact with each other. The fluctuations are not coupled. Imagine n, there are n numbers, n is an integer, n numbers of oscillators. Imagine all of them are just oscillating. In the volume is about the Planck volume, which is 10 to the minus hundreds centimeters cube. And none of those particles, the oscillatory fields, are just interacting with each other. If they were, we could observe. Or we may choose, we may find a solution. And we could know what dark energy is. We don't know yet. I have some theory for it. So to the some final value, well, I may say a tilde. Okay, you know the reason why. And from some time, let's say TR, T sub R, corresponds to the radiation. So A squared, right, over 2 equals, I would like to call it gamma R. Gamma R. Okay, I want 8 pi g over 3 rho radiation 0 1 over half times t. I just multiply both sides to here equals that. So what we see, A of t for radiation case that it is 8 pi g over 3 rho radiation 0 root. So this is 1 over 4 t to the 1 over half. What we see that the scale factor, the expansion or the distance function between 2 points in space, it is not required or have to do a galaxy. There are points actually in space. I will show it in relativistic notations afterwards in the future. Is, well, proportional. Okay, that's right then. Gamma r t to the 1 over half. That is my function. So I'm going to use this notation again. Are we recording, by the way? We are recording. Yeah. So, which is equal, well, let's say this is radiation now. 1 over half gamma r 1 over the root times itself, 1 over gamma r t to the 1 over half. Chats 1 over 2t. So the Hubble parameter for the radiation dominated universe is 1 over 2t radiation, and the radiation, the time it takes is 2tr. Oops, the Hubble constant. If you measure it for today's data, didn't I write it here? Well, it seems like I didn't. It's about plus or minus years. It's expected, by the way. It's expected. So the horizon, the stage, is multiply both sides, CTR, which is C over 2H TR, right? I'm going to leave them alone. So the physical length, which is actually the entire horizon of the radiation dominated universe, we don't mean that there are no matter, no, there are, but the radiation density is dominant, okay? This is 2 CT TR. You can find it out, the length of it. Careful about the units. It's all. I will summarize again in the next video before continuing with the closed universe. Okay? Let me show you one more thing, the second order equation, and we will finish that. It was actually a double dot minus 4 pi, let's say this is plus 4 pi g over 3 rho of t a of t equals 0. I divide every side by the inverse of a of t. So this is our equation. Okay. You have your solutions from here. If it were constant, then it is quite visible. It is oscillatory, harmonic, e to the minus some constant time t, and I'm really tired. Well, speak English is actually requiring more force. Even you speak well, or even you used to speak every time. It's not easy. Physics is also hard. Physics is also hard. So this is 1 over a cube. Okay, whatever, we're going to solve this. Yeah, that's a lot today. I'm done.